Okay, so remember the last video you watched was regarding just density curves and in general. So here I just want to remind you of what a density curve is. Here you have pictures of 3 different histograms and you have curves drawn over each of them. And the curves are just drawn on there to use as an estimation for how the distribution looks. So yes, you could have a symmetrical curve just like this lower one here. You could have an almost another symmetrical one here. It's just a little flatter. It's more spread out than the one down below. Or you could end up with a density curve that is also skewed. Okay, so density curves are very important in statistics. In particular, we're going to end up having a very special one, which is called the normal curve or normal distributions. Okay, normal curves describe normal distributions. They're symmetric, single-peaked, and bell-shaped. They all have the same overall shape. They're described by giving the mean and the standard deviation, and the mean and the median are always at the center. So in order to have a normal density curve, basically what you're going to end up having is you're going to end up having your graph in some way, and you're then going to draw in your curve like this. Okay, you see here that the curve is symmetrical. It's also bell-shaped. It's single-peaked. We would have our mean and our median here at the center. We could give the mean, whatever number that's going to be, and the standard deviation to describe it. Here you have two identical, not necessarily identical, but two of the same kind of distributions. The difference between them is essentially that their mean and their median is at the same place for the mean and the median. However, the standard deviations are different. The one here up at the top, the standard deviation would be larger than the one at the bottom. The standard deviation at the one at the bottom would be smaller because it's a higher peak and everything is kind of more squished closer towards the mean. Here in the top one, the mean is larger because it's more spread out from the mean. Here's another example of that same thing where you have a flatter, more like a hill kind of a curve versus one that is very tall. You notice that their means are lined up right above each other, but the standard deviation in the first one is clearly bigger than the standard deviation in the second one. Remember, we have two new symbols. We have mu and we have sigma now for mean and standard deviation. Okay, here again is another example of some different normal distributions. You can see there's a whole bunch of different ones with different colors on them. You'll notice that the purple one has a standard deviation of 1.5. It's the shortest one, it's more spread out. The blue one has a standard deviation of 1.25. It's a little taller. And as you go through, the green one gets even taller. You notice that its standard deviation is getting smaller. The yellow is even taller, so it has a smaller standard deviation. And the red one is the tallest of them all with the smallest standard deviation. They all have the same mean, which was 0 in this particular example. Okay, so some more examples of normal density curves. You'll notice at the top there are 3 different ones similar to what we kind of showed a few minutes ago. Okay, where you have a mean of 15 for all of them. You also end up having different standard deviations. Which one do you think has the standard deviation of 6? Good. The maroon one has a standard deviation of 6. Which one do you think has a standard deviation of 2? Good. The blue one, or the navy blue one, has a standard deviation of 2. So the green one would have a standard deviation of 4. Okay. At the bottom, you're going to see that the means instead are different. The mean for the blue one is essentially at 10. The mean for the green one is at 15, and the mean for the maroon one is at 20. The standard deviations in all of them in this case are the same. So you could end up with different curves that all have the same mean but different standard deviations, or you could end up with 3 different curves or more than 3 different curves that have different means but the same standard deviation. Where are you going to see things with, or sets of data with normal distributions? Heights of people in the classrooms or in a room, weight of people or grade level, IQ scores, standardized test scores like the SATs or the MCAS. You're always going to have people with low scores. You're going to have people with generally grouped together, and then you're going to always have people with higher scores. Body temperature, and anything where you have repeated measurement of the same quantity. So here you have a curve, okay, and this curve is a normal curve. Now when you're drawing a normal curve, the first thing you always want to make sure you label on your x-axis is the mean. So remember, you're going to have your mean here, mu. Then you're going to have 3 spots to the left and 3 spots to the right. And all of the 3 spots to the right, when you go from the mean out to that spot, it's going to be mu plus 1 standard deviation. If you were going 2 marks out, it's going to be mu plus 2 standard deviations. If you go the 3rd mark out, you have mu plus 3 standard deviations. Going to the left, very similar in nature, you have the first tick mark as mu minus 1 standard deviation. You have the second at mu minus 2 standard deviations, and the third is mu minus 3 standard deviations. Okay, so whenever you have your normal curve, this is how you are going to draw them. You're not going to have necessarily these symbols underneath, but this is where you begin in order to do that. So if I gave you a specific example where it says the heights of females in the class is normally distributed with a mean of 64 inches and a standard deviation of 1.5 inches, draw a normal curve to represent this data. So to draw the normal curve to represent the data, you have to go down here to your curve. You would first have drawn in the curve. Okay, you're going to do your best to draw a symmetrical one. You first graph the mean, so you would label here as 64. And then go to the right 1 standard deviation. So you do 64 plus 1.5. Remember, we're getting that information from up here. Your standard deviation is 1.5. Your mean was 64. So mu was 64. Sigma was 1.5. So we're going to do 64 plus 1.5, which would be 65.5. You're going to do 2 standard deviations plus 64. So 2 standard deviations will be 3, so this is going to be 67. You're going to do 3 standard deviations added to the 64, which would be 4.5. Which would be 4.5, so you're going to add 4.5 to there, so you're going to get 68.5. Okay. You then want to do the same going to the left. So going to the left, you are going to end up having your first tick mark as being 62.5. Oops, sorry. Your next one, again, going to the left, another standard deviation, so you're going to end up having 61. You go to the left again, and you're going to end up having 59.5. Okay, so now you have all of your standard deviations, or 3 of your standard deviations to the left and 3 of your standard deviations to the right labeled. So that's all you have to do in order to just draw your normal curve and label your standard deviations and your mean. So just make sure you remember you practice drawing your standard normal curve, and you're going to then label it. So if I gave you another example where I told you that your mean was 50 and your standard deviation was 10, you could go over and you could label your mean at 50. Your next one would be 60 and 70 and then 80, and you would go to the left 40 and 30 and 20. You can think of standard deviation as almost like your scale where you're going down and up by the same amount. There is one special empirical rule we call, or the 68, 95, 99.7 rule, that you should know about when you're doing normal curves. And basically what this means is that it's just where most of your data ends up lying. So here, if you look at the one on the left, 68% of your data is going to fall between the one standard deviation to the left and one standard deviation to the right. Okay, if you look over here, two standard deviations in both directions, 95% of your data is going to fall. And three standard deviations from both sides is going to be 99.7%, which is almost all of your data. But just be careful because you do still have a little tiny bit of each of your tails that isn't represented in that. So because of those percentages, that's where we get the name of the rule of 68, 95, and 99.7. Okay, so that it's just a way for you to kind of estimate how much of your data is found in between all of the different standard deviations. So let's do a couple example problems. If I have a graph and I tell you here, obviously you have your graph, I'm telling you your mean for height of women is 64.5, so you can tell that your mean is 64.5, and that your standard deviation is going to end up being 2.5 in this case. So what percent of women are found between the height of 62 and 67 inches? Well, if you look at the bottom of your graph here, from 62 to 67 inches is one standard deviation away in both directions, so that must mean that 68% of women are found between those two heights. What percent of women are between 59.5 and 69.5 inches? Well, 59.5 is two standard deviations away to the left, and 69.5 is two standard deviations to the right, so that must mean that those are 95% of where the women are. What about between 64.5 and 67 inches? Well, that one's a little harder. You have to be careful because that's not really giving one of our main three, which is 68, 95, or 99.7%. So we want to go from 64.5 to 67 inches. Well, remember, between 64.5 and 67 inches, that's only half of our 68%. So if I know that between 62 and 67 is 68%, well, I'm going halfway. So what's half of 68%? Good, it's 34% of women. So sometimes you're going to have to do some breaking up of the 68%, the 95%, and the 99.7%. So why don't you try the 67 and the 49.5 inch one? Okay, so in order to do this part, remember you have to look at between 67 and 69.5. Well, that's kind of, it's between your one and your two standard deviations above the mean. So think of, okay, this is two standard deviations above. So I know that from 59.5 to 69.5, that's 95% of my data. I don't want all of that. I almost want to take half of it though. So if I divide that by 2, I'm going to get 47.5%. But that would be from 64.5 to 69.5. I don't want between 64.5 and 67 inches, which I know is 34%. So if I subtract 34%, I end up getting 13.5%. So from 67 to 69.5 inches is 13.5%. So again, you may have to do a little manipulating of your 68, 95, and 99.7 numbers. Okay, if you look in your textbook, there are more explanations with this rule. This rule is very important and we're going to be using it a lot, and you're going to be doing some practice problems now using this rule.